Good morning. I don't know about you, but coffee and donuts are essential parts of my breakfast. But what if I told you that they have something in common besides both being delicious? Well, in the world of topology, a coffee mug and a donut are essentially the same. Let me explain. Topology is a branch of mathematics that studies the properties of geometric objects that remain unchanged under continuous transformations, like bending, stretching, or twisting. One of the key properties that topology examines is the number of holes an object has. In the case of the coffee mug and donut, both have exactly one opening. Topologically speaking, this makes them equivalent or homeomorphic. But what does topology have to do with anything besides my breakfast? Well, topology isn't just limited to physical objects. It can also be applied to data. In topological data analysis, or TDA, we explore the shape of data, uncovering patterns and insights that are not so obvious through traditional methods. Here's how it works. First, we gather data points and measure the distances between them. For numerical data, proximity is often measured using a metric like Euclidean distance, what you might recognize as the distance formula for math class. But the datasets we work with in TDA often exist in high-dimensional spaces, far beyond the x, y, or even z we're used to plotting in algebra class. Imagine trying to picture a dataset with dozens or even hundreds of variables. It's not something we can easily see. So how do we make sense of this high-dimensional data? We need to connect the dots within a certain distance threshold, where 2 points connect to form edges, 3 points create triangles, and 4 points form tetrahedrons. These shapes combine into simplicial complexes, which capture relationships between points in multiple dimensions. Sequences of simplicial complexes are constructed by gradually increasing distance thresholds, and topological features that persist across different thresholds, like clusters and loops, are the most significant. This can give us some incredible insights into the data. So how does TDA work in the real world? Well, the noisy nature of brain data makes TDA an ideal tool to use to study brain activity. In a recent study, researchers used TDA to map structural brain differences in Alzheimer's disease, discovering that different types of Alzheimer's are associated with distinct patterns of brain degeneration. By identifying these differences, TDA could pave the way for earlier diagnoses and targeted treatments, an exciting step forward towards improving lives. So the next time you enjoy a coffee and donut, remember that a simple opening can change the world.